Everybody can see the screen, right? And I'm writing backtracking.
Yep. Yeah, yeah.
Cool. So basically today we do not have to learn anything new. Whatever you have learned in recursion is basically used. We'll just see few more advanced stuff, right? Or let's say a few more variations of recursion that come up to backtracking, right? So we start with this problem first. I'll share the problem link. It's called non-decreasing subsequences. Right. It might just seem like it is actually. Like there is one trick that I want to share in this problem, and this is warm up to recursion. Just try to think about this problem. Actually, really easy. Okay. Whatever you've been doing, it's just the same thing. Right. Pick not pick. Try. It's non-decreasing subsequences. 8 chord. Right. Mm, Give an example was 2 4. Let's say 2477. Right. So okay, give me the pick not pick. Pick and not pick. Right. As usual, you'll be maintaining what a current, right? Current which stores whatever current configuration you have, right? And you don't need any duplicates. Remember, right? I'll share the link again. Uh, so we are solving this problem currently. It's called non-decreasing subsequences. Take 2 minutes, understand it. Right. Or better, I'll actually just explain. You can just look at the screen. Right. So basically, given a array of numbers, you have to return all the subsequences that are non-decreasing. Right. And understand there's difference between non-decreasing and increasing. Non-decreasing it where duplicates are allowed, but you shouldn't decrease. That's all. Right. You can stay equal or increase, but you shouldn't decrease. That's called non-decreasing. Right. And increasing might have been you cannot allow duplicates as well. Like this is a non-decreasing sequence, while this is increasing sequence, right? This is not increasing sequence. Remember, increasing sequence, everything should be increasing. In non-decreasing sequence, whatever happens, just don't decrease it. You can keep it equal or increase it, right? So let's see. And I think this should be a bit intuitive, right? Of pick not pick. You start with index 0, right? You start with current as empty. Now quickly tell me what is pick and not pick here. Duplicates are to be considered.
Append, append it to the current array
Yeah.
and pass it, increase the index and
Sorry.
increase, like append the current index,
Yes.
like of the value, and
Yes.
then call the recursion function for index plus one.
Yes. Current of I. Then you okay. Let's call the recursive function as helper of you call it on I plus one because you don't have to repeat it, right? And you pass the current there, right? And when you come back, one second. Yeah. And when you come back, you pop out, right? Pop, right? Basically, right. So pick is easy, and when do you actually accumulate it? So always understand that all these problems are exploring some subset, right? So all these numbers are exploring some subset. And do you remember the subset tree that I once drew for 3 elements? How do you start? You start picking from the 0th index, then you go down, then you pick the first index, then you pick the second index, then when you reach the third index, you know that these are all the subsets, right? Do you remember this logic? Right.
Yeah.
And why is that? Because this splits into two, this splits into two, because you have two in the first, or I think this is the first element, right? So this starts with like this. So it starts empty, right? So you have option to pick the 0th element here, either pick or not pick, right? This is the option to pick the first element, right? This is second, right? And when you reach the, and basically, so second you can either pick not pick, right? Pick not pick and pick not pick, right? So but the index passed is something like this, right? Initially when you have empty, you start with 0 index, so you have option between 0 and this is 1, this is 2, right? Here you have an option for the second element. This becomes I is equals to 3, and you know that this is the place where the subset is completed, right? So basically at when I is equals to 3 here, or let's say when I index is equal to whatever, let's call this num. So when it is equal to num dot size, right, num dot size, do you know that you have reached a position where you have some kind of subset, right? But you're lacking something while picking it, right? There's a condition to pick it.
I mean, you need to check if the last value that you put in the array is
Yes,
going to be smaller or
yes.
equal to the.
But what if the array is empty? You can still pick anything, right?
If that is empty, we can do directly current or append.
Yes. So basically, if length of current is 0, or let's say current of -1 is, this should be smaller than or equal to, right? Num of index. If any of these satisfy, you can pick the element, right? For picking, right? I hope this is understood. This is the whole idea of the problem, right? Last element should be either smaller or equal to the current element that you're picking, so that's non-decreasing, right? And if currently the list is empty, you can just pick it, right? Because there's nothing to compare with, right? Okay, this is all right. And when this happens, you have to check one more thing. They say that the size of the subsequence should be at least 2, right? So you just check one more thing. If this is nums dot size, and if current dot size or current dot length of current is greater than equal to 2, you push it to answer dot pushback current, or answer dot append current, whatever you take, right? So you reach the last step where you can finalize your subset. You check the current is at least length 2, you pushed it to the answer, right? So this is your pick part. Now remember the not pick part, I taught you something how to avoid duplicates, right? When you are not picking this, you entirely skip it, right? So basically if you are picking 2 and 4, let's say you are picking 7, so you pick 7, and in the next event also you might pick 7, right? But in 2 4, if you plan not to pick 7, you don't pick this 7 as well, you just skip it entirely, right? Because we have to avoid duplicates, right? So here if you chose not to pick it but to pick this, and here let's say you chose to pick 7 and not to pick this 7, you see that these are having duplicates, right? So you choose not to pick it. Like if you choose not to pick it, you just skip it entirely, right? Yeah, Dishan.
But yeah, is it given that the same elements should be grouped together?
Same elements should be grouped together? No.
Like in the description, I don't see it anywhere.
So
Like if we are skipping it like this,
hmm,
if we are like avoiding duplicates like this by skipping same elements,
yeah,
how would we skip it if the same elements are far apart?
yes. So yeah, this is where we modify the not pick as well, right? So what we say that, okay, actually you can, yeah, that's the problem, that it's not lying like this, right? So array can be like 2 4 7 uh 3 7, right?
Yeah.
Right. So here what you can do is, right, here first of all you won't be picking 3 anyway if you are picking 7, right? So so actually what I actually figured it out was, you don't do the not pick here as well, like let's say 2 4 7, so 7 pick, right, and 3, let's say you didn't pick, so 7, what I did was you either pick it, right, you either pick it, or when you have to not pick it, you can just skip it, because wait, give me 1 second.
Manas, do we need this condition? Because I don't think we need to use it, right? Because even if there are duplicate elements, would our answer change? Okay, our answer will change.
Yes,
Okay.
right.
That is
Because if
if
you
there are
plan not to
duplicate
pick it
elements.
and plan to pick it once, if plan to pick it and not pick it once, answer will become the same.
Yes, yes, yes. But the thing is here, order also can be random.
Yes,
And
order can be
7,
random, yes.
and you can't change, and you can't sort it because the order matters.
You
The
cannot
order.
sort it as subsequence, yes. See, what I'm saying is, you don't do a not pick as well uh, if num of I is equal to, or you only do a not pick when num of I is not equal to current of -1. Why is this there? Let's understand it with this example. Actually, let's remove this for now.
Minus does current of -1 mean the previous element?
The last element that you have selected,
Okay.
this current array, right, which contains the
Uh,
selected elements.
okay.
Well, I'm sorry I joined a bit late. Could you just tell what question we are discussing?
Yes, I'll send the link back again. So we are discussing this question, right? So don't read it. I'll tell you what it is. So basically, you're given a list num, right, and you have to find the various non-decreasing subsequences out of it.
Okay, but subsequences, right? Yeah. So
Yeah.
sets.
Yes.
Okay, good.
So we discussed the pick part. So you can pick elements if the current array that you are maintaining, or the current list that you are maintaining for the subsequences is empty, or the last element is less than the current element that you are planning to pick or not pick.
Understood.
This if condition. So you do the normal append, call the recursive function again, and pop. So when you are not picking it, right, what you do is, see, we were trying to skip, right? So like this is what I was explaining currently. So when you pick it, it's fine. You do the normal thing that you do. When you don't plan to pick it, right? When you don't plan to pick it, you do not call the not pick function. You do not proceed like this. And you know, do not plan to you plan to not pick it, and this element is, let's say, equal. So it's not for this, it's for this element, right? So you pick this element, you came to the next I, right? Now in this iteration, you either pick it. If you pick it, it becomes 2 4 7 7. That's fine, right? If you do not pick it, you do not proceed forward from do not pick. Okay, try to understand this. If you do not pick it, you do not proceed forward. Okay, this condition. So if you're not picking it, basically the number that you are iterating through is equal to the last picked element, right? So you do not proceed forward. Right, what will happen if you do that? So 2 4 7, if you pick a 7, you move forward. Right, if you plan not to pick it, you stop here. Right, now you will say that, okay, then you cannot generate any sequence like 2 4 7 8. Right, you'll tell me that, okay, this is not possible because you just stopped this from happening, right? But I did not actually stop it. Can you backtrack and understand that when we didn't pick this 7, but we picked this 7 instead, we got 2 4 7, right? And then this can help us generate this configuration. right? I am only stopping this when you have already same element picked, right? This is essentially uh, the thing that I told you to do when they are in arranged like this 2 4 7 7, right? Like what I mean is that here this even this poses a problem, like what Dishant said, right? But doing this will actually avoid that as well, right? Try to think. You have currently, let's say, 2 4 7 in your list, right? When you plan to pick it, you make it 2 4 7 7, right? When you plan to not pick it, you don't go forward. No, you just trace back. You don't even go forward. Okay. Now what happens when you have picked 2 4 and okay, this came from, realize that this came from 2 4, right? 2 comma 4. This came from 2 comma 4. What can also come from 2 comma 4 is just 2 comma 4 when you plan not to pick 7, right? So let's say you don't plan to pick 3 as well, right? Here, let's say here also I just removed that step. Here also you don't plan to pick 3, but you plan to pick 7. So here you can come up with 2 4 7, right? And can you see that you are not repeating this? Now if you have continued this part, it would have been 2 4 7 again, right? But you didn't do this. You did not repeat it, right? You stopped this from happening, and you allowed the other configuration to do that for you. It's a bit confusing to understand, but try to understand it. By skipping it here, you are actually taking it somewhere else, because this 7 has to appear somewhere else again, right? So this 1 2 3 picking actually takes place of this area where you do not pick anything after 7. Give me 1 second. Give me 1 second.
But yeah,
ये दो
Yeah.
है same answer.
but how will we know? Okay, since 2 4 since 7 has a duplicate value, we are
Hmm.
stopping after it if we're not picking it.
Yes.
But how will we know? Okay, this particular element has a duplicate value. Are we making a map beforehand? And if so,
No, no,
then
no,
why
no,
not
no.
just sort?
No,
Sorry,
see, how are we skipping it? See how are we skipping it? The current number that you are trying to choose, right? The current number that you are trying to choose, if it is not equal to the last element pick, then only you are proceeding. Basically, what I'm saying,
okay, so we're doing strictly increasing.
yes.
हाँ
Okay.
What I'm trying to say is, let's say it was something like this. You picked 3, you picked 4, you picked 7. You didn't choose to pick 3 now. Now you are choosing between 7. So if you choose, you move forward with, let's say there were few numbers ahead. So if you choose, you add all these to your list and you move forward, right? If you do not choose to pick it, you do not move forward, because
But
the
then,
current number that you're picking was equal to the last picked number.
then what about, let's say if we had an 8 afterwards? So 2 4 7 8 to generate new.
अब कुछ
Yeah,
नहीं कर
that's what I said, right? See, initially, when 2 4 7 was generated, it was generated from 2 4, right? So at one way it went 2 4 7, the other way it went
2 4.
right, and when
Oh, okay. And now वहाँ पे वापस हो
क्या
गया.
है?
Okay,
when
got
this
it.
7 repeated, this became 2 4 7, right?
Cool. Understood. Yes.
So it is
So
taking
if
care
it,
of repetition.
I'm
Yeah.
sorry for disturbance, but if it becomes 2 4 7 again, then does it like backtrack back to like the right hand side of the tree, or does it like continue here with another like node with 2 4 7?
Yeah, it continues with another node. See,
Okay, so
yeah, see, the whole idea is that, see, at one point you are generating 2 4 7, right? And at another point also somewhere we were generating 2 4 7, right? But what happens
yes.
that this only proceeds in pick. So something gets added and it's back. Right. This doesn't proceed with a not pick. Right.
Okay,
And what I'm meaning to say is, whenever this picks something, see, in this example, when it was picking it was picking a duplicate with it. Right. Here, this 7 was at other index. Let's say this was at x index or yth index, but this was at x index. Right. So it will proceed this way. Right. And this might proceed just 2 4 7 without picking anything, or it might proceed like 2 4 7 8. Right. which you see it's not duplicate anyway. Right, I'm not allowing this to generate to proceed like 247 without picking anything, because this
Sure.
is going to generate duplicates.
But yeah, can you show the code for the not pick condition where it is cur of -1 is not equal to I?
Okay, wait, I'll actually paste the code here
Oh,
so that you understand. So I'll just paste the pick not pick part. I hope it will be visible. It's visible?
yes, yes.
Yep.
See, if current size is 0 and number of index greater than the last element picked, you push it inside the current, you call the recursive function, you pop it back again. If not pick, again, if there is no size, there is nothing to compare with, so you can just pick it anyway, right? And if the number that you are currently picking is not equal to the last picked number, then only you proceed with the not pick fashion. Not pick fashion, current doesn't change, index increase, right? So there's a condition to do this, right? Even for the last sheet, I think where it was combinations 3, you can use this for not pick fashion. You don't have to use the while iteration thingy. This should
So,
work.
let's say, can you illustrate it with an example of, let's say, 2, 4, 7, 8, 7, 8, like that?
2, 4, 7. Let's say 2,
8?
4, 7, 7, 8.
Okay.
Okay.
No, like 8 is also repeating case, like that.
8 is also a repeating case.
So, like 7, 8, 7, 8, something like that.
Okay. So you start with empty. Okay, you either take 4. Let's say you start with 4, right? You take 4, 7. You do not take 7, so you just take 4. So here you take 4, 7, 7. Pick one. Okay. Let's do one thing. I'll draw a pick at the left so that you're not confused. So 4, 7, 4. Here pick is proceeded, but not pick isn't. Again, same reason. Right, last number is equal. Now here 4 didn't pick 7, right, but it will pick the next 7. So it didn't pick the first 7, right, this one, but it picked the, so this is the first level, you're choosing the first element, this is the second element. So you pick the second element, making it 4, 7, right, and you will not pick it as well, not pick anything. Now you're choosing the third element, 8. So if you choose it, it becomes 4, 7, 7, 8. If you don't choose it becomes 4, 7, 7, right? If you choose it here, it becomes 4, 7, 8. Don't choose it, becomes 4, 7, again 4, 8 and 4, right? And in the last position, I'll write all the elements here. So if you choose it, it becomes 4, 7, 7, 8, 8. If you don't choose it, it becomes 4, 7, 7, 8. If you choose it, okay, this was not supposed to be. Okay, this was.
I think you skipped a node. 4, 7 का एक और node आएगा जहाँ पे 4, 7 not pick हो रहा है after the first level.
Okay,
the
no,
second
this won't happen actually. Right, see, for this node, pick will be done, not pick won't be done, because we are choosing 8 and last chosen element was also 8. So not pick won't be done here for this node. Same reason, you're choosing 8 and the last chosen element was also 8. So you won't go not pick, you'll just go pick. Now here you can go both pick and not pick. So it becomes 4, 7, 7, 8 and 4, 7, 7. Here also not pick won't happen, only pick will happen. So it becomes 4, 7, 8, 8. So 4, 7, 8 is not repeated, right? Not pick won't happen. Yes, here both can happen, 4, 7, 8 and 4, 7, right? In 4, 8 just pick can happen, 4, 8, 8. Not pick cannot happen because again last element similar. In 4 both can happen, and I think we are not repeating anything.
Manas, so in theory, you're technically just pruning one branch so that duplicate
Yes.
elements who are not found, right? So
Exactly.
technically, we could also apply this to the pick function where we prune one specific portion. That also could work, right? Or is this really applicable to the not pick
You
part?
can do that. You can. I think you can do that to pick as well, but
Yeah.
again, I find this more convenient actually.
Yeah, actually. Yeah.
Right. I think what you are saying is also work, but again, you have to figure out how it will work.
Yes.
Right. But this is actually this will take care of duplicates always.
But yeah, like in this one, 7-8 is also a possible answer, right? So that
Yeah.
there will be one more level to this tree, right?
Yes.
One more above
Yeah,
4.
one more level above here, where 4 is not picked.
Understood.
Right. But let's just say, okay, actually you can just eliminate this branch and actually remove all the 4s. Right.
Oh,
Then
right.
you
Okay,
exactly.
damn, bro,
Right.
that's nice.
Just consider this as an example. Right. Then you'll understand. So just remember this. Whenever you're not picking, you don't explore the not pick branch if the current element we're choosing between to not pick is equal to the last element that you had picked. Right. So again, like I am trying to avoid a case that looks like this for 7-7. Right. How? I am avoiding to move in this direction. I can move in this direction but not in this direction.
So, okay, understood. Multiverse. But like, I understand how it is working, but I don't understand why it is working.
Try out some examples.
Okay, okay.
Right, some
Like,
examples.
why are we doing this norm index minus curl dot back?
Again,
I'll try.
yeah, this, yeah, I understand. Like this just removes duplicate. Right here, I proved how it does that. Right, it removes it by not exploring a branch. Like again, let's say 4-7. You explored 4-7-7. Right, but you won't explore the not matching part. Right, because let's call this 7 first index and this second index. Right, because when you don't pick this first 7, you will pick it later with this 4. Right, so 4-7.
Right.
Right, so you see 4-7-1 and 4-7-2, these are matching.
Matching,
Right,
right,
so
okay.
you won't explore this branch, is what I'm saying.
Understood now. Yes.
Right, just try out some examples, print it yourself, then you'll understand better. Right, so again, if you have doubts, you can again ask me. You can create a thread with this and ask me to explain it again. But let's just quickly rush through problems now. Okay, now we are going to do backtracking, and very standard lead code problems of backtracking are, I think all of you know, it's Sudoku solver and n queens. Right, so both of them are really interesting, and I hope, yeah, this is not a solution, right? Yes. Yep. So this is the first problem. It's Sudoku solver. Okay, there is some other questions called valid Sudoku. So this is lead code Sudoku solver. Right, and again, like backtracking is just an extension to recursion. Right, it's nothing very something new. Right, again, like it's not very standard. Like in recursion, we followed a standard template, pick not pick, but here it's not something standard. Right, again, you can actually generalize it. You can still generalize questions like Sudoku solver and n queens. Right, I'll tell you how. But again, there will be some catch at every place. Right, so basic way to do Sudoku solver. So what is Sudoku solver? It's basically you're given a grid, right, and you're given some numbers, and I hope everyone knows what a Sudoku is. So in a Sudoku, you shouldn't be having, you put fill numbers from 1 to 9 in cells. So in one row like this, you should be having 1 to 9 exactly once. The count should be exactly 1. Right, in a single row, 1 to 9 should be exactly once, and in a 3 cross 3 grid, right, not every subgrid but every adjacent subgrid, 3 cross 3, you should have 1 to 9 exactly once. Right, all these three conditions satisfy. Right, so basically in this question you are given a Sudoku. So Sudoku contains of 9 3 by 3 grid arranged in a 3 by 3 fashion. So this is a 3 by 3 grid here. So again, here, and like this. Right, so basically this is 9 cross 9. Right, and you're given a few numbers and you have to fill the rest of the numbers. The question says that a valid Sudoku always exists provided with these constraints. Right, and you have to find any valid Sudoku. Right, now again, I'm not sure if exactly one exists. Okay, so how do you solve it? This is solved using like this is proper example of a backtracking problem. Right, and how exactly? So let's say your first cell of Sudoku has number 5. Right, and this is actually very time intensive. All problems like this, right, all backtracking problems where you have to explore almost all configurations, very time intensive. Right, but somehow things boil down. Okay, because one thing is dependent on the other, so it's not exactly how you think. This question doesn't take like 9 So if you say that you can put 9 numbers in every cell and you have a total of 81 cells, so 9 numbers per cell, like 9 numbers to choose from, the time complexity becomes 9 raised to the power 81. If you look at it plainly in terms of combinatorics, but of course this is very big, right? For instance, this is the maximum time complexity that you can handle. This is way bigger than this, right? But thing is, due to this, due to the conditions that I wrote, right? Due to these conditions, things become interdependent on each other, right? So the time complexity reduces. So here, how do you solve it? You take, let's say the first cell is filled, okay? You come to the second cell, right? You come to the second cell and you try to fill some number, let's say 1, right? First you check whether filling this 1 is applicable. How? You check this row shouldn't have 1, there shouldn't be any 1. You check this column, there shouldn't be any 1. You check this 3 by 3 subgrid, right? There shouldn't be any more 1 here. If everything is fine, you proceed, right? Now you check, now you try to put 1 here and check the same thing. You will realize that you just put 1 in the last cell, so you cannot put 1. You try to put 2, you do the similar checks. If the check fails, you proceed with the next number. Again fails, you proceed with the next number. You keep on doing it, right? Now it's 5, now it's 6, 7, 8, 9. Now after you have surpassed all the values that can be filled in a single cell, you go back to 1. You tell him that now, okay, 1 is not feasible. Okay, you have to change the number. You have to change it to 2 now. And again, once you put 2, you check, let's say everything works out. You again start with 1 here. 1, 2, 3. You check every number here, right? Similarly, you keep on doing it for the entirety of cells in the Sudoku, right? You check, you put number here 2, right? You check it for 4. Then let's say 4 works out. You put you check, take another cell which is empty, right? And mind that some cells might be filled already, right? You take another cell. You start checking from 1. Is what 1 viable here? Is 2 viable here? If is 3 viable here? So can you understand that by doing this, you can solve the entire Sudoku? And once it is not viable, you change the number, right? You keep on changing the number, right? And when you have reached the limit, you backtrack, right? You backtrack and you change this number now. You change 4 to 5 now. Now you see if 5 works, right? Similarly, you do this for everything, each and every cell, until you find a working configuration, right? And the question says you will find a working configuration, so this works. Right. Now, I'll give you a very small template sort of like how to proceed with these problems. So, one thing that you should make is like functions that return a boolean, right? And you can name it whatever. What I use OK, right? So, what you do is you pass some parameters and you pass the value that you're trying to put here. So, the parameters are like where you are filling the number and what number are you filling. So, basically, you pass the row, column, and the number that you're trying to fill. So let's say row and column are is the cell that you're trying to fill in the Sudoku, and the number is the number that you're putting there. So this function should return whether it's valid or not, right? It should return is it valid or not, right? And how will it do it? Again, same thing. For that row and column, it will check whether the number exists in the row, exists in the column, or exists in the subgrid that the row and column is in, right? If it exists, if the number already exists, it returns false, saying no, it's not valid, right? If it exists, it returns false, says that no, you cannot put this number already exists. If it does not exist, right, it returns true, that this number can be put, right? So this is the function that you'll create, right? And it will just go and check it, right? Creating this function is really simple, right? Again, for the grid part, you might have to work a bit, right? The subgrid part, try to figure it out, right? Otherwise you can always ask me, but try to figure it out. But this is like how you can check whether this is how you can check whether it is in some column or row. So basically 0 to 9, and value is the value that you are checking. Ij is the row and column, right? Current. So you iterate through all the columns of ith row, you iterate through all the rows of jth column, and you check whether any of those contain a value, right? then for subgrid you have to do something else that you try to find out. If it matches with any of this, like any of the row or column contains the same value, just return that no, this is not valid anymore. Go on, Aditya.
What if we use sets to check if it is in the set or not?
Yeah, you
Like
can
that.
do that as well. I initially solved it with a map. You can do that as well.
Okay.
But yeah, but the thing is that constraint here is so small that you don't even have to worry about that.
Oh,
Right.
okay.
I tried doing that. That the code became very spaghetti very quickly.
Yeah, I
Right.
can imagine. Like you'll have to pop out of pop the
Yes.
values out and all.
Yes,
Yeah, yeah.
exactly. So the better thing is just to make the OK function. Right. Now I'll tell you how to do the solver now. Right. Now once you have the OK function which says placing here is valid or not, and this judges it based on the board that you pass it. Okay, in the board you have to keep filling values. Right. Now see, now once you have the OK function, see how easy it becomes. Right. Now you call the solve function. Right. The solve function basically solves the board. Right. And again, you don't have to point what part of board you are solving currently, because it will again find out how. You run a loop from 0 to 9, all the cells. You run another loop for column from 0 to 9, right? And if, so basically in this question, if board of ij is dot, that means you have to fill the number there, right? So okay, you found the cell where you have to fill. Now what to do? Now you have to pick the elements that you have to fill, right? Now you start from 1, this is 8 actually, inclusive, alright, 0 to 8. So these are the indices. The numbers that you have to fill are from 1 to 9, right? Okay, now you found the candidate number that you can fill, right? Now you check whether it's okay to fill it there, right? If it's okay to fill this number in ij, right? If it's fine to fill it here, right, what do you do? I'll just continue. I think I'll continue here. Okay, so if it's okay, what do? You feed
Just
it to the
take
board. First
Yeah,
you feed it to the board. You say that okay, this is okay to it's okay to assume that this value can be put here. Again, understand that later on it might not be possible for some other configuration. Let's say you put 2 here, you put 5 here, you put 7 here, but later none of the numbers were possible here. So you might have to backtrack back again here, right? And you have to make this 3, and you might have to choose these all over again, right? So what you say, you will say that okay, if it's okay to put it here currently, if it's okay, you put the number there, then you solve it again. You solve the entire board again. This thing, you are calling it back again recursively. You just change the cell and you are solving the entire board again. Now what happens, can you understand? When you filled the current cell, when this is filled, and this you filled currently, the next solve function will skip these 3 cells, right? Because it's filled for it. It will try to fill this cell based on what values you have already filled, right? Or was already there according to the question, right? So it will start to solve the board again, right? And let's say and tell me, when can you say that the board is solved? The board is solved when you break out of this function, right? When you explore all the cells and you find that everything is filled, right? Everything is filled, you say that it's solved, right? So outside this function, where this loop ends, the outer loop end, you will return true. You will return true, saying that you iterated through all the cells and all the values are filled, and those are only filled because everything was okay. That means you have solved the board. You return true, right? Now, if this returns true, that means everything after it is solved. So you return true back again. I hope this you can understand. If you are able to solve the board after this cell, after putting this value in this current cell, if you are able to solve the board, you return true, right? So basically, let's say you are solving the board, you solved the last cell. It said that okay, the number you put is okay, right? And the next iteration, the solve function will go through the entire board, finding the first cell that has not been solved. It won't find anything. It will come outside and return true, saying that okay, the entire board has been solved. It will return true to this cell. This will return true to this cell, right? And it will keep on happening. It will keep on happening. It will keep on happening until the first cell that you called, right? So this will actually get true, right? And once it gets true, it says that okay, this number is fine here. You can go back, right? You can return true back again. right? But if it's not true, then remember the condition that I told you. If it was not true for this number, it's not true to place any number here, you send a false back, right? Right, but not right now, because you have not completed iterating through all the possible values that was here for the cell, right? So for this, okay, if this was not true, you don't return false right now. You reset the board now. You reset the board to dot, and in the next iteration, next value is picked. Right, try to understand this. Right, you reset the board to dot, and the next iteration, next value is picked. What happened when you have explored all the values? This board becomes empty and you trace back. You backtrack to the previous cell. Right.
Wait, so the board variable just represents one cell, right? It doesn't represent the whole board, right?
Sorry,
If
board
I'm-
of IJ. Yeah, my bad.
Okay, yeah.
Yes. So like this is what I was doing in code, and this one part is remaining. So after you have explored the entire loop and you are not satisfied, you didn't return from there, understand that if you will only return if a value is satisfied at that particular cell. If no value is satisfied, you know that it's not possible to solve with any of the current configuration, so you return false. Right, where do you do it? Okay, this is just the code part. I'll tell you what is happening exactly. I take a big row, right, of cells. Now you filled some 5, 6, 4, 9, 2, and here you try to fill some number 3. Let's say that the only possible number to fill here was 3 according to constraints, but again there was a 3 here already present in the board, which you cannot erase, right? So you say that okay, 3 is not possible to fill here. You try 4, 4 is also filled. You try 5, 5 is also here. You try 6, you try, let's say 7 was also here, 8 was also here, and 9 is already on the board. So what do you say? You say that okay, I tried all the numbers. Where is this happening? This is happening inside this loop. Here, this is happening here. It is trying all the numbers, checking if it's okay, right? But once you break out of the loop, right, and if it's okay, it's trying to put it there, right? But right now nothing has been put because no number was okay, right? If it's not okay, it comes back to this, right? What happens? It returns false. 2, where does it return false to? When 2 was okay, so when you put the 2, this must have been okay, right? You did okay for 2 at that current cell, which would have been with the respect of this cell j minus 1. It said okay, it's fine to put 2. So inside you tried to solve the board again, right? But the board returned false from here. The next cell returns false. So it's not possible to put 2 here anymore. So you go with a different number now. Where is this happening? See, if the solve is not true, you are resetting the board and the loop starts back again, and you take a different value now, and you set the board to a different value now, right?
Yeah, why do we need to reset the board? We can
Because-
just set the variable to the next loop variable, right?
Because what will happen when you have tried all the combinations? When you've tried all the combination, it won't be overwritten, right? Basically,
Yeah, it's just one copy. Yeah, understood.
yeah, understood, right? So when this 2 and you have tried every number here, so you don't want to leave it with a 9 and go back.
Right. So
you want to
we
erase it.
reset before returning false, right?
Yes, you reset as soon as you come out. It's exactly like the current thing that we did, like current dot push, go there, current dot pop.
Right.
ईमेल से
So
तो भेज
the-
दो क्योंकि
But like
ये चीज़
you
करने
reset
वाला ना
before
मैंने बनाया।
return false.
मैं मेल चैट कर दूंगा
You
तो
yes,
बस
you reset only when it returns false. You do not
तो
reset when
ये
it
इस
returns
पर
true.
डाला।
I'm
जिस
saying you
sheet
reset
में डालो या
before
बस
you
जो तुमने लिखा उसका photo भेज
return
दो।
the false
Yes,
value.
अभी
yes,
sheet
yes,
में
yes,
डाल।
yes, that you are true about. So we reset the board if the current configuration doesn't work, because there are 9 different configurations for a certain cell. You reset it 9 times, and if none of those work, then you return false. This is the whole part. Right. Again, try to
What
implement
Just
is
it.
send me the mail
Right.
time
and
complexity
the
for
picture
this?
of people.
This time, yeah, that's what I told you, right? If you look at the worst time complexity, it is 9 raised to the power 81, which is not possible at all, right? But in backtracking and recursion problems, basically, that you cannot determine the time complexity plainly, because sometimes
Understood.
it's like a tree where you are not actually exploring the entire tree. You are breaking off from places, right? So you cannot
It's not
guarantee.
defined for each
It's not defined.
sub-problem.
Yes, it's not
Not
defined.
sub-problem, but like yeah, it's not defined
Okay,
for each particular problem. I see.
Contents
Yes. But basically, if the constraints are very small, like 9, 8, 15, just go and write the recursion. Because even if it goes like here, it's huge. It's 9 raised to the power, but mostly it will be 2 raised to the power. So 15, 8, 9, anything will work. Right.
Understood.
Right. But
Also,
again,
one
yeah,
more thing is in the previous page, if you can go to the previous page,
yeah.
uh, you said we have to write a return true outside of the two loops, outside of the two parent
Yes,
loops, right?
wait, I'll make it here.
Yeah.
So for I, for j, and in this line, you are writing return true.
But then, matlab, in the first, let's say you're placing the very first value, right?
Yes.
If that you'll also have a if solve, then you'll set the arguments. वहाँ पे तो return true अपने आप आ ही जाएगा ना. So why do we need this extra
This
return
is, yeah, this is because when you have solved the entire board,
true, right?
when you have solved the entire board, this, see, what is after for I and for j? There is a if, right? If the board is not
Yes.
solved, if it is equal to double this, right? So if each
Yes.
and every element of the board is filled, you won't be going inside anything, right? In that case, you'll come out of the loop, is what I'm saying.
Okay. So this is for the very last value.
Yes, for the very
Okay.
last cell. So for
Understood.
when every element in the board has been filled, which means that it was only filled when you check whether it was okay or not. So if every element is filled, the board is complete, the Sudoku is solved. Then you return a true from here to the last cell, saying that it's solved. This says this solved, it's solved. It just keeps on returning back.
Understood.
Yes. So this is the Sudoku solver. There is a valid Sudoku as well. That is a bit easier than this. You can go and check it.
So when we are not able to solve the Sudoku, where do we return false?
Yeah, so what happens that for a particular cell you are looping through all the values, right? 1 to 9. So what happens that once you loop, come out of this loop, right? Look here, you are choosing the value here, right? So once you are thorough with choosing all the values from 1 to 9, right? And say, let's say you choose 1 and it's not okay. You choose 2, it's not okay. You chose 3, it's okay. But later you chose explored few more cells. There it backtracked back and told you it's not okay. Sorry. So you chose different values again. Not okay, not okay. You explored the entire loop. None of the value you can place it here. So you return false. Right. This is what happens.
Okay.
Right. I understand this a bit confusing because we are returning something 3 times. Right. But understand that the first return is if all the cells are filled, there is a return true. Right. Now if it's not filled, you are choosing between values. Right. And if certain value is okay, and if you can solve the board again with that value, you return true here. Right. Now if all the value has been picked and you cannot solve, you return false here. Right. At one point, if you can see the tree, this true is going to be returned here, right, after the board has been filled, because this solve calls the function. So if the last cell calls the solve function, the last cell is filled, you cannot go inside it because this will never be true. You will return this true, and this true will be caught here by this solve, and this will return true, and this will be back again. The last previous cell will catch this true and return true. Its previous cell will catch this true, return true. Right. Try to solve this problem, picturize it. This is a really good recursive problem, and not, it's really hard as well. Try to solve it. After you can understand, you can picturize the Sudoku tree in your mind, you have essentially learned backtracking. Right. It's actually a hard problem. Try to solve it. Right. Any doubts you ask me, any doubts you have right now you ask me. Right. This can be solved in different ways as well. How I solved it initially was I mapped what all has been visited and what all has not been visited, and what is the next cell that I am visiting. Again, it was a bit complicated. Okay, this is the most easiest solution that I'm telling you. You iterate over all the cells, then you iterate over all the values that possible in that cell. You check whether it's possible to place it here. If it's possible, you solve the board again. Right. Again, just try it. Again, you have any doubt, you ask me. I've seen a lot of you are solving questions in different ways. That's also fine. Okay. But I'll advise you to stick to what I am telling you, because later in DP we are going to use something really very similar. Right. Then you'll have no doubt in understanding DP. Right. Any doubts on this question? Because I think we have more questions as well.
But yeah,
Yeah.
even if you like explain the time complexity thing, like
Hmm.
even so, is this the optimal solution, the most optimal solution?
No, this is not the most optimal solution, to be honest.
Okay.
But you
Uh,
won't require a better solution because the difference will be
uh,
very low.
And like optimality only matters if it's passing. Like the scores only matter for lead code, right? For companies, it doesn't matter.
It doesn't matter, to be honest. Yes. See, it matters in interviews where you don't have to code it. Okay, don't code the most optimal answer always, but know what is the most
Uh,
optimal answer. You have to explain it to them that okay, what I wrote here,
mm,
like you remember the recursive linked list approaches that I told you about. You tell them that this is recursive and this has a more memory overhead than an iterative one that I understand. But this is lot more simpler and smarter,
so,
right?
like, just for curiosity, what would be the best solution for this one?
The best solution will be what I actually did in the first go. So there you keep
The
track of
map one.
INJ, yeah. You keep the track of what next cell you have to be filling, right? Plus you map everything, right? So I had a map of row, map of column, and map of grid,
So
right?
the
So I,
OK function will become constant then.
yes, OK
Not
function will become
constant, but
constant. No, it's
yeah.
actually constant. Yes, if you use unordered map, it's constant. So you just have to check that row of I of value should be 0, right? Column of
Map is map is like set in Python, right?
No, dictionary.
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 Yes,
Okay. How
and
will it be constant time?
hash table.
Unordered map.
Okay.
Yeah,
Yeah. We'll discuss it later.
hash table I discussed with you, right?
But still, इसमें we are checking 2-3 times, right? पता
Yeah,
नहीं.
so 2 3
Think
times
about it.
3 into 1.
हाँ.
Okay, anyway, let's see the next
हाँ.
question that I
I'll
sent.
think of it later.
Yeah, yeah, cool. See the next question that I sent to n queens. Right. Now this has a bit change. Instead of solving it now, you have to report the number of solutions. Right. So again, I think it's easy. Instead of reporting counting true and false, you found that you can count the number of true that you can get. Right. So what will happen is for one configuration, again you do the exactly same thing what you did for Sudoku, right? You put queen in one cell, right? And one thing is sure, right? For every row you are just putting one queen. So n queens, I hope everyone remembers how to play chess. So if when you put a queen somewhere, you cannot put a queen in the same column and row, right? The row part can be handled very easily because every iteration you are placing a queen in one row. So row check is not necessary, column check is necessary, right? So you check the column whether, so what happens is when you place a queen, right, when you place a queen, you go to, you place it in one row, and remember that in how you solve n queens is a really important problem. Okay, both Sudoku solve n queens. N queens was asked in Wells Fargo on campus placement interview last year for my batch, right? So please, these problems are really important, please solve it. Okay, even if you don't solve hard DP problems, graph problems, street problems, it's fine. These are the very basic and standard DSA problems, please solve it. Please be thorough with these problems, at least the sheet that I give you today, right? So how you solve n queens, it in the first row you keep it, and you have an array which doesn't represent the grid, understand? It represents, we call it config, it represents a list where for every index is the row, right? And you write what column have you placed the queen on. So this current configurations look like this 0 1, and this is in fact 0 1, right? Now if you plan to place the queen here, your configuration looks like, so this is 1, so in the first index you put 3, right? Your configurations look like this. Now I'll give you a valid n queen solution. So this is a valid n queen solution. The configuration looks like so this is 1 3 0 2, right? I hope everyone understands this. Okay, this is not something really hard, but it's just a bit smarter way to represent a 2D grid, right? Because this is an only hood because you, every row you're just placing one element, right? Every row you're just placing one element, right? Any doubts, ask me. Again, you make a OK function which says is placing a queen valid, right? Is placing a queen valid, right? If it's valid, you go forward, right? So here it will look again something like this. You solve for all the rows, right? Or you can actually, here right now you can have a recursive function, let's call it helper, which says what row are you solving and what is the config right now, right? So whatever row you are solving, you can put again the board size is exactly the same, so whatever the config size is n, right? is what you'll go through. So you can put a queen in all n columns, right? So from I to 0 to n minus 1, you can put a queen here. Now you check, is it okay to put my queen in this row and the column is I, provided this is my config, right? If this is okay, you, let's say you have an answer and answer is initially 0, you can count the number of answers that you can generate. Okay, you can count the number of answers you can generate from, again, calling the helper function with row plus 1, and you update the config, right? Config of row is I, right? Config of row is I, and let's say your config initially contains -1 everywhere, right? Saying that nothing, this has not been touched. Okay, again you can handle it in this different way as well, and you change the config to this. You try to calculate the answer by passing row plus 1 and config. See, this is how we came here with row and config. You pass row plus 1 config. When you are done with that, you reset your config of row to -1, right? You can reset the value. Again, same pattern how we did for Sudoku, right? But instead you are counting the answers now, right? Now again, what happens when your row reaches config.size, which is actually n, right, or length of config.size, you return 1. You say that okay, the answer is possible. Why? Because you placed all the queens and all the rows and you came to the next row. That means that all these are valid, right? So you return that okay, this is valid, return 1, right? So similarly, there can be multiple answers which can be returned like this.
Manas, I understand the answer part.
Okay, so
Like, what are we, why are we returning 1?
we are returning 1, saying that okay, this is a answer. Like if you place your queen in this current config, let's say you placed queen somewhere like this, like okay, let's say this is an n into n board, we don't know, we placed queen in some configuration initially, right? And after this you try to place queen somewhere here, right? Like from here, if you are exploring this row currently, right, or not this row, you are exploring this row currently, right? You'll try to place queens all the way from here to here, right? All the way from here to here,
Yeah.
right? And it might happen that you might get answers here as well and here as well. It might happen. Let's just say it happens, right? So how many answers are you getting for this row? You are getting 2 answers, right?
Right.
And let's say this 2 was possible when queen was here, right? In the row -1 row, right? Let's say when you placed your queen somewhere here, which was possible, you were getting 3 configurations which was giving you an answer.
Yeah.
Right. So here the answer will be total of 5. Can you understand? This generated 2 answers. This generated 3 answers.
Okay.
Right. And how did you generate it? You kept placing queens. Right. You kept placing it. And once you ran out of rows to place, you basically know that this is a valid configuration. You returned 1.
So then you're adding to.
Right. So let's say in last row there are 3 solutions to queen being placed here. Right. If you place a queen here, there were 4 solutions. Similarly, this queen being placed here could generate these configuration. So if this was 3 and this was 4, this queen generates 7 answers. Similarly, this queen might in some configuration generate 10 answers, right? And similarly, you have to it keeps backtracking. The answer keeps backtracking back up. Right.
So you're trying to return like the number of possible solutions as well.
Yes, this is the question.
Okay.
This is n queens too, so you have to return the number of possible given integer and return the maximum number of distinct solutions to the n queens puzzle.
Right. Got it.
So for basically we are trying every possible combination. Now remember, even in Sudoku we were trying that, and even in Sudoku there might be multiple possible answers, right? So actually even you can change the Sudoku question to find the number of possible answers, right? And again, instead of returning true this time, you can return answer. If it's true in the very end, you just return 1, and you keep adding the number of times you're getting 1 from the last or the I plus rowth choice when I becomes row.
Instead of if condition of solve, we again just do answer plus equal to.
Yes, you do
all
answer plus
the
equal
board.
to.
Yeah.
And basically when you have to return false, you return a 0.
Right.
right?
What?
So
So basically, instead of returning true, we return 1 so that it gets added to the number of solutions.
exactly, yes. So I'll paste the code sort of. Let's see if you can understand this. If row is config.size, you return 1, right? No, the count, which is answer is 0. So column 0, column config the sign, column plus plus. You place the queen in this column, right? So config of row is column, right? Like how I explained you how config is made, right? If it's okay to place it here, you do count plus is equals to increase the row and pass this config, right? Then you reset the config. Understand that when you cannot get anything out of this current placement, the count is going to be 0 and 0 is going to be returned, right? Any doubts in this? This code might seem simpler than Sudoku, but under the hood, lot of things are happening, right? Take a moment, right? And an OK function, you have to code row, column, and diagonals, right? Now,
So
hmm,
in this one, like before, what we were doing was as soon as the answer was becoming, the solve function was giving true,
ye return back, yes,
we returned. But here
yes.
we are just updating a variable, right?
Yes, yes, yes. There, as soon as we find a working configuration, we say, okay, it's possible, we return back, right? But here we are not just finding one answer, we are finding multiple answers, right? So we are counting it, right? So every time configuration works, we keep incrementing it, right? And this works like, uh, how do I say? This works like a tree again. So if you place queen here, and this allowed you to place queen here and here, and this allowed you to place queen, of course this won't allow you to place here, let's say it allowed you to place queen here and here, and this queen allows you to place queen here and here, and this queen allows you to place queen here and here, right? And let's say this queen has a valid answer, this has no valid answer, this has one valid answer, this has one valid answer. It will return both here, the sum is 2 here, and this will return both, sum and sum is 1, and here it's 3. So you'll say, okay, total answers are 3. Can you understand? This is also forming some sort of tree, right? The number of different paths that you're exploring, or the number of different configurations you're exploring, whatever, like some of them might lead to an answer, some of them might not. Whichever leads to an answer, you return 1, and in the end, you keep counting, right? And in the end, you just report the count, right? Number of things are happening under the hood. Try to understand this, right? You'll have the slides, and but I think this will be all white, right? So again, look at this code for a minute, and what's the time? It's 10:07. I'll give you a question. We won't discuss it fully. We'll just understand it a bit, right? And then we'll end. These are the questions that you're having for the sheet as well. Understand it fully, please. If you have doubts, again, keep asking me. Keep it, opening new threads, right? These questions are really very important, right? Sorry, I sent a submission. One second. Actually, have the submission with you as well, I think. Just for now, don't save it with you. This is the original problem. It's called unique paths 3. Right now, this is a sort of BFS problem, you can say. It's breadth first search grid, but you can explore everywhere. Right. You can explore in all 4 directions. Constraints are really small, so you don't have to worry about it, about the number of paths that you're going to get. Right. So the question says, I'll explain you the question. Don't read it fully. So you're given a grid, you're given a starting point, you're given an ending point. Both of these can be anywhere, and you have some obstacles. You have some obstacles here and there, right? Now what the question says is, you have to find the number of paths such that you start at starting point, you end at ending point, you visit all the cells exactly once, no repetition, right? So here, this is a bad example actually. So let's say you start here and end here. Now you can see that this is a valid path, right? This is a valid path. Remember that you have to visit all the cells. Right. What else can be a valid path? This, 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 something like this. Right? There can be so many number of paths, right? If you take all the combinations, right, or everything. Seems very similar to the ends queens question. Yes, all of these are backtracking, right? Exactly. So again, do exactly what you are thinking right now. You take the starting point. You move in all four directions, but remember this time you have to maintain visited array, right? You are not to repeat it again, repeat the same cell again. Also, you are not entering any illegal cell, right? So look at this.
Wait, so visited area as in, let's say I had a path from A, B, C, D, like that. And now let's say I have another path, E,
Oh my
F,
God,
G.
okay.
But
I was
now
like, wow.
I could also have another path, let's say E, B, C, D.
Yes.
So E, B, C, D will not be valid.
No, A, E, B, C, D will be a different path.
It will be a different path, right?
Yes.
So like, but since B, C, D were a part and A, B, C, D were a part of a different.
Yes, so
of
this is
our
not valid.
text.
This is not valid. B is being visited twice.
No. What I'm saying is, since ABC were there already have been visited once
Yes.
with one path, it's fine, right? If we
Yeah, in different paths it's fine.
Like it,
Okay,
we all
okay,
are the
cool.
same.
You can have
basically
Yes.
it should be like a Eulerian, like Hamiltonian.
Yes,
I don't
yes,
know,
yes.
but one of those things.
I get the feeling. It
Everything
should be
happens.
there. See, it can be. These are two different paths: A, B, C, D, and A, C, B, D. These are counted as two different paths. Okay, so had this been the answer would have been two, right? So look at this. So paths. You're finding number of paths from I and J, such that your grid is given. You have a visited array which says this cell is visited already, and you have the number of nodes that is remaining that you have to visit. Right. Don't count how many you have visited. Start from that this many nodes is that you have to visit. Right. And if you run out of the grid, this is just to check if you run out of the grid. You don't have to run out of the grid. And again, when you are going left, down, up, right, you don't check that you are going in the out of the grid or not. You let the base condition handle it. Right. So if you are running out of the grid, come back. If the grid is a blocked path, it's a blockage. -1 will be blockage. You come back. If it is visited, you come back. Right. Otherwise, you go there, you explore it, you mark it as visited. Right. You mark it as visited, and so you mark visited of ij as 1. Right. You make remaining nodes minus. Again, you don't have to reset this because this is not passed by reference. Remember. Right. It's minus. Even in Python, you won't have to reset it. In Python, only lists are passed by reference. Okay, people, you might have doubts in Python. That in Python, all the lists are passed by reference. And if you don't want it to reference, if you're adding list to a list, always do a deep copy. Right. Otherwise, they're always passed by reference. Remember. Right. So you do remaining nodes minus. You do visited of ij plus. And if now the ending node is marked as 2, so if grid of ij is 2, right, if grid of ij is 2, right, then you have to check if remaining nodes is 0. You are to visit the last ending node of the grid only when you have visited all the nodes. If this is 0, you will say that you will return 1. Why? Why 1? What is 1? What is the 1 is that a path ends here. This is a valid path. Else you go back, you still return back because you cannot come to the ending node unless you have visited every cell. This is an invalid path, right? But before returning back, you mark visited I of j as not visited now. So visited of I of j becomes 0 and you return again. You return 0 basically from here, right? And everything goes like that normally. When you go left, you change this function ij, right? This has already been visited, so again you'll go left, you call the same function again by changing the coordinates left, right, up, down. Done. In the end, what do you return? You return the total sum of paths that you're getting, right? So from left you are getting few paths, right few paths, this few paths. You just add everything and return the count, right?
115.
In this one, there's not a lot of pruning, right? the only pruning can happen is when either you are stuck in a position.
Yes,
Point
yes, yes.
four.
The only
Or
pruning happens something like when you are exploring like this and you have nowhere to explore,
understood.
right? So
Okay,
you have to
And
backtrack back here and go explore something else.
understood. Or you're like surrounded by obstacles.
Yes, yes, yes.
Okay.
And there might be a, I think there is a test case where there is a starting point here and there is an obstacle completely. So the answer is 0,
0. Okay, nice.
right? OK function will change. Yes. OK function, see here, OK function is this base condition, that's all.
Yeah, like if it can traverse, that's
Yes,
all.
yes. Right. So, okay, this was the last question I wanted to discuss. So, this, if you have understood all this question, not right now, if you have understood later when you have solving the problems, you have understood like a very huge chunk of backtracking. Okay, so these are really important backtracking problems, and please by heart them, understand them. Right. You might be asked them directly in the interviews because this is even in your Corman textbook. Right. At least the inquiries. Right. So, that's it. Thank you for joining. I'll put the problems plus this PDF there. Right. I think it's a bit late today. Sorry.